So, the gas laws. So we've been looking at solids and liquids mostly to this point. We've been looking at solid metals. We've been looking at liquids in terms of solutions, of having like ionic compounds dissolved in them, or sodium hydroxide, like at acids and bases dissolved in them. So we've worked on solutions as concentrations, working up molar concentrations of liquids and all that sort of thing. We haven't really talked about gases yet, other than we're talking about polarity, which is like a big thing in this particular chapter. One of the things, if you remember, I said about a lot of non-polar substances tend to be gases. And the reason for that is non-polar substances don't really interact with each other very strongly. Polar molecules have a slightly positive side and a slightly negative side, and they tend to hold together. Like water is polar, it has a slightly positive side where the hydrogens are, and a slightly negative side where the oxygen is. And so they hold together, and they're held together with some amount of energy. So it takes a lot of energy to break that interaction. And so because it takes a lot of energy to break that interaction, they stay interacting in a liquid form. And so when we see charged molecules, like ionic compounds, you have a full positive charge and a full negative charge, sometimes more than just one, sometimes 2 or 3 or 4 or 5 or 6 charges coming together. And we've seen that those are very strongly held together. Remember salt, NaCl, we needed to heat that up to like 800 degrees before it turned into a liquid, because that interaction was so strong. And other ionic compounds, like it was like magnesium oxide was one of the examples we had in the lecture. We needed to heat that to almost 3,000 degrees to get those interactions to break so that those ions could move around. Well, if you have completely nonpolar molecules, there's basically nothing that's holding these things together. The interaction between them is extremely weak. And because the interaction is so extremely weak, they tend to just fly about as gas molecules. You have to reduce the energy to get them into the liquid phase, and you have to reduce them even more to turn them into solids. And so we haven't really looked at gases or figured out how would we even calculate the concentration of a gas. We haven't even thought about that. Liquid is fairly straightforward. You could just measure its mass and then figure out its density, and then you could get how much it weighed, how much its volume is, all that kind of stuff. But with a gas, it's kind of hard to think about. So what are when we think about gases, how do we usually like calculate the amount of a gas we have? What are some of the things we use to calculate the amount of gas we would have? Like if I have pressure, very important. Yeah, because remember, a gas is different from a solid or a liquid in that no matter what container I put it in, it fills it, which is a little weird to think about. But if I have a gas cylinder that holds like 100 liters, if I put just a little bit of gas in it, it fills it up. So if I look at let's say I put my gas molecules in there, it's full. But I can put more gas in it, and I just put more molecules in it. And I put more gas in it, and I just get more molecules in it. And so the more molecules of gas I put in that cylinder, the volume doesn't change, but what does change? The volume of the cylinder does not change. It's still 100 liters, but something does change. What measurement does change?
The pressure.
The pressure, that's absolutely right. The pressure is going to go up. And the more gas I put in there, the more gas, the higher that pressure is going to go. And we're going to learn that pressure is due to the fact that these molecules are constantly moving. So we know that all molecules move a little bit, right? They're all sort of at least vibrating slightly. But in a solid, they're moving so slowly that we can't really detect it. In a liquid, we can actually sort of see them moving around. They're moving around more quickly. But in a gas, they're moving so fast, they're just bouncing all over the place. And when these gas molecules hit the side of a container, that increases the pressure. So the more and more collisions these gas molecules have with the sides of the container, the higher the pressure goes. So if that's true, if we add more and more molecules, we're going to have more and more collisions of molecules with the size of the container. So as N, which would be the number of moles of gas, goes up, my pressure goes up. And that makes sense, right? Because the more gas molecules, the more chance it's going to interact with or bounce off the sides of the container, the higher my pressure is going to go. What about if I increase the speed of the molecules? If I increase the speed of the molecules, are they going to hit the container more frequently? If they move more quickly, are they going to make more collisions with the side of the container?
Yes.
Yes. What would make the molecules move faster?
Airs?
What's that?
Air?
Air. What do you mean? That would be like adding more gas. Yes, I mean, adding more gas increases the pressure. What if I have just the same number of molecules, but I wanted to make them move faster? How would I do that?
Heat.
Heat, exactly right. Because we know the higher the temperature, the higher the thermal energy of the system, and the more kinetic energy we give to the molecules. And so they're going to move faster. And the faster they move, the more likely they are to come in contact with the sides of the container. So as temperature goes up, pressure has to go up as well. Even though we have exactly the same amount of gas molecules in my container, if they're moving faster, the pressure is also going to go up. So there's only three things we can measure when it comes to gases. We can measure the volume. The volume is just the container that they're in. So we can measure V. That's fairly straightforward. What size container did you put them in? We can measure the number of moles. That's N. We can work out the number of moles. And we can measure the pressure. We can also determine what the temperature is. So these are basically the four things we're looking at when we deal with gases. The volume, basically the amount of gas, the pressure, and the temperature. So these are the four things that you're going to be varying and see what effects they have on each other. So basically what you're going to be doing in this experiment is deriving the gas laws yourself. So have a look, and we'll have a look and see what these gas laws are. So the first one that I want to look at is Avogadro. So I've mentioned that Avogadro's law, or Avogadro's number, is something that, I think we should probably stop talking about in chemistry class because it's just confusing. But Avogadro's law is something else. Now, Avogadro noticed when he was doing reactions that involved gases, what he would do, and you would have done this experiment in lab yourself. Unfortunately, we don't get to do this one because, COVID and everything else. But he noticed he was doing a reaction. And so he wanted to collect the amount of gas in a reaction. So what he did was he had his reaction vessel here with a long tube. And then the gas would come out and it would go into a test tube that was upside down and filled with water. So this was, let me just fill this with water. Water is blue. Yeah, so this would be all filled with water. So we had it upside down and filled with water. So when the reaction inside this chamber, so you would add chemicals in the chamber and that would produce gas. And so the gas would flow out and in to the tube, and the gas would displace the water. So as he did this reaction, he would get more and more gas, which would fill up the top, and it would push out the water at the bottom. So this would be the water at the bottom, and this would be his product, the gas product at the top. And he noticed that when he added twice as much reactant into his reaction, so he would get twice as much product. When he got twice as much product, the volume inside of here would be twice as much. And so he figured out that the amount of moles of gas is dependent, it is directly related to the volume. So we say it's related to the volume. And then he expressed it with this particular equation. So if I have N1, so just some amount of, just like, let's say 1 molar, it would have a volume of V. Now, if I had twice as much, twice as many moles of gas, if I had 2 moles over here, my volume would be 2V. And so the ratio would be exactly the same. So if I have 1 mole of gas, and that gives me a volume of V, if I have twice as many moles of gas, my volume is 2V. And so that is a direct relationship. Moles to volume is a direct relationship. And that is the equation he used to describe that. So what you're going to do in this experiment is change the number of molecules of gas and see what effect that has on the volume. And then we're just going to plot these. Now, any questions on how Avogadro did that? I realize that these drawings are just hideous, but basically that's how you would do a gas reaction. You have it bubble into a tube, and we just measure the volume of the gas in the tube. Basically, the tube looks just like the burette we used for doing titrations, except just imagine the burette turned upside down and filled with water. So the gas would come in from the bottom, bubble up to the top, and push the water out. So does that make sense, that there's a direct relationship between moles and volume? Do you see how that works? Yes, no, maybe you do.
Yeah.
I mean, it seems fairly straightforward that there would be a direct. You put twice as much gas in there, and it's going to push out twice as much water. It's going to displace twice as much. So the volume is going to be twice as much. But remember, that's at a constant pressure. So when he's doing this reaction, it's all at 1 atmosphere of pressure. And so the pressure doesn't change. So if the pressure doesn't change, the volume is going to have to change, because the gas is going to be taking up space. And the more gas you have, the more space it's going to take up. And that's what Avogadro showed us. So that's one you're going to be doing. Next one is Boyle's law. And Boyle's law showed that there's a relationship between the pressure and the volume. That if I increase the pressure of a gas, and I allow that gas to expand, it's going to increase the pressure of the gas as well.
You mean the volume?
Oh, yes, sorry, yes, the volume. So basically, if I put if I put the same amount of gas and I squeeze it into a smaller volume. So let's say, so I have the same, so in this particular instance, so in Avogadro's law, I was keeping pressure constant. Now in Boyle's law this time, I'm keeping the amount of moles constant. So I have the same amount of gas, okay? I have the same amount of gas. So what happens, I have the same amount of gas. So I have, N equals 1, however much that is. Same amount of gas. Let's say I put it in a piston. So I've got a piston here. And I'm pushing it down. So I have the same amount of gas, but I'm pushing down in this piston. And so let's say I push it down so that the volume is now half of what it was. So I push it down and now the piston is here. What do you think happens to the pressure now that I've squeezed that gas into half the volume?
Increased it by 1/2.
Increased it by 1/2, or so it would go up by 1/2, or it would
Decreased by 1/2.
well, just would it go up or down? Basically, is what I'm asking. So if I make the volume smaller,
It would go up.
the pressure would go up, right? So as my volume goes down, my pressure goes up. Because basically I've taken the same amount of gas, and when I squeeze it, there's now more gas molecules in that smaller space. There's more molecules per space than there was before. So now that I've reduced the volume, those molecules are going to hit the sides of the container a lot more quickly because the container is now half the size. The same is true if I do it in reverse. Then what happens when I squeeze the piston, instead of in, I pull it out, and so that my volume goes up. What's going to happen to the pressure this time?
Lower pressure.
Exactly. It goes down. So if I let the piston go the other direction, if I then pull it out, so now my volume goes up, now my pressure goes down. So instead of it being a direct relationship, with Avogadro it was a direct relationship. The more gas I had, the more volume I had. That made sense. Now what we have is called an inverse relationship. That actually my volume is related to 1 over the pressure. It's an inverse relationship because as my volume goes up, my pressure goes down. As my pressure goes up, my volume goes down. So they're inversely related. Yes, their question.
I just confused. You said in the beginning when the volume increased, the pressure increased. And now you said when the volume increased, the pressure decreased. I confused.
No, with the I have a single amount of gas. I have the same amount of gas.
Okay.
If I keep them in a larger container, the pressure is going to go down. If I have the same amount of gas and squeeze them into a smaller container, that pressure is going to go up. Because the larger volume means that those molecules are going to hit the sides of the container less frequently than if I have them in a small container. They're going to hit the sides of the small container more frequently. Does that straighten it out? Because every time we do one of these experiments, we have to keep one thing constant. Either we have to keep the number of moles of gas constant, or the temperature constant, or the pressure constant. We have to leave one thing the same, and then vary one other thing and see what the effects are. We vary everything at once. We can't see what the relationships are. So in the first example with Avogadro, we kept the pressure constant and changed the amount of gas. And in this instance, we keep the amount of gas constant and change the volume. So each time we're changing just one thing at a time and seeing what effect it has on the other things. Okay?
Okay.
Okay. So, yeah, so if we have a piston and we push it down, we make it a smaller volume, the pressure is going to go up. And if we make a larger volume, the pressure is going to go down. So we're going to do that experiment as well. And then Charles' law came along. And in his instance, he wanted to see what the relationship was between temperature and volume. So in this instance, N is constant, and the pressure is constant as well. So N stays the same, and P stays the same. Now what we're doing is varying temperature and seeing what effect it has on volume. And so in this particular instance, we can think about a balloon. So a balloon can expand and contract, right? So if I have a balloon, sort of draw a little balloon here, put a little tail on it, and so I put my gas molecules in it. Let's put some gas molecules in it. So I put some gas molecules in there. So what happens if you put a balloon in a freezer? Has anyone actually done that? If you take a balloon and put it in a, lower the temperature way down. Has anyone ever taken a balloon and put it in liquid nitrogen? That's really fun. Has anyone ever done that?
Pop.
What happens?
It would pop or expand.
In fact, the opposite. If you cool down, if I take this balloon and I put it in some liquid nitrogen liquid, that's at minus 178 degrees. So it's very, very cold. And so what happens to those gas molecules? They're moving around, they're creating pressure, they're moving around. Then I cool them way, way down. So they slow. Now the movement of them slows way down. What happens to the volume, do you think? Remember, they're moving more slowly now.
It will shrink.
It's going to shrink big. Actually, it's hilarious when you put it in. Basically, it shrinks to nothing. It looks like it's empty. So I put it in liquid nitrogen and it shrinks. The volume goes down. So if the temperature goes down, the molecules move around much less quickly, and my volume goes down as well. Oops. Volume goes down. Where's my eraser? Yeah, my volume goes down. Now, if I take that same balloon out of the liquid nitrogen and I just leave it on a table and let it come back to room temperature, what do you think happens to it?
It expands.
Yeah, it expands. It gets bigger. And if you leave a balloon in a hot car, it expands even more. That may have happened to you. Like you get a whole bunch of balloons for like a birthday or something, and you leave them in a car. Well, this doesn't really happen in the Bay Area. But let's say you're in Phoenix or something in the middle of August, and you've got a whole bunch of balloons in the back seat of your car, and you forget about them. And the car heats up to like 130 degrees or something. A lot of those balloons are going to explode because the volume gets bigger and bigger and bigger because the molecules are moving faster and faster and faster. So they're going to expand until eventually they just pop. And so this works when we keep the pressure constant. So the pressure in the car doesn't change. It's still atmospheric pressure, but the volume of the balloon gets bigger. So as the temperature goes up, the volume goes up. So is this a direct or an indirect relationship?
Direct.
That's direct, right? That's a direct relationship. So if we were to plot that, and you guys will be plotting this today, we'll be doing a lot of diagrams. So when we plot that, what do we put on the x-axis and what do we put on the y-axis? One of the things is we're going to be, one thing we change and the other thing we measure. So one thing we change directly, we do the changing, and the other thing we measure as a result of that. So
The temperature for X.
That's right, that's very good. Yes, because I'm varying the temperature in those reactions. I'm dialing in very specific temperatures and seeing what the effect is. So T, we say, is the independent axis, because I am independently determining what I want those values to be. I'm the experimenter. I will independently determine that I want A, B, C, D, E, and F temperatures. Y is the dependent axis, because the value of Y is dependent on what I choose for X, right? We don't know what Y is going to be. It depends on whatever X is going to be. And so I'm going to plot my temperature, and my volume is going to be whatever I measure it to be. So Y will be the dependent axis. And if things are directly related, what kind of line should I see if these things are directly related? Should it be curved? Should it be going up and out? Should it be going down and away? What kind of line should I see?
Increase up.
Increase up, yes, and it should be relatively linear, right? Because if the temperature is if the volume is directly dependent on temperature, when I plot them, I should see something like this. And then I get a line. So basically what this tells me, remember the slope of the line is y over x, right? And so the slope of this line tells me how y is dependent on x. And if it's a direct relationship, if it's 1-to-1, the slope of this line should be 1. If the volume goes up twice as much for every time I change the temperature, the slope will be 2-to-1, or 3-to-1, or 1/2-to-1. Whatever it is, the slope of the line tells me what the relationship is between volume and temperature. Does everyone remember that the slope of a line is y over x? You remember that from math class? Hopefully you do. There's going to be some math in this one, I'm afraid,
Yes.
boys and girls. Yeah. So that's Charles's law. So again, Avogadro's law will also be direct, because we increase N, we increase the number of moles of gas, we increase the volume. So we're going to plot moles against volume. Charles' law, volume is directly dependent on temperature. So we're going to plot temperature on the x-axis and volume on the y-axis. Now let's look at Gay-Lussac's law. Clear this out. Gay-Lussac, or Gay-Lussac, another genius French chemist. So many. So he noticed that now if you kept volume constant, so this time he's got a constant volume. So basically what he's looking at is if you have a hard container, ooh, that's ugly. If you have a hard container, so again, you'd have like that gas tube. So I've got a gas tube, I seal the top of it. I put in a certain amount of gas. So let's draw some gas molecules. So I have a certain amount of gas molecules and they're moving around. So my volume stays the same and the number of gas molecules stays the same. So not only is V constant, N is constant also. Now what I'm going to do is vary the temperature. So I'm going to vary the temperature. So when I increase the temperature of this container, the molecules are going to start moving more quickly, right, as they do. What's going to happen to the pressure?
It'll increase.
It'll go up, right? If my temperature goes up, the speed of the gas molecules moving around and hitting the container, they're going to hit the container more frequently because they're moving faster. And so the temperature goes up, pressure goes up too. Now, if I take that container and I dip that in liquid nitrogen, so I cool it way down, now the molecules start moving much more slowly. So they're moving much more slowly. They're much less likely to hit the sides of the container. It'll take a lot more time for them to get there. So there'll be less collisions on the walls. And so when my temperature goes down, what happens to my pressure?
Goes down.
My pressure goes down too. Yep. So again, I have a direct relationship here. As temperature increases, my pressure increases. So what am I going to plot this time? So I have a direct relationship between, I'm changing the
Linear as
temperature.
well.
What am I going to put on the x-axis?
It's going to be the temperature.
Yes, because I am changing the temperature. And then what am I looking at its effect on?
The pressure.
The pressure, exactly. And so as I plot these, I should see something like this. See, I should see a direct relationship. And I go all the way down, and it should go through the zero. It should, because we know at zero, what happens to all the movement of molecules at 0 Kelvin? So absolute zero. What happens to the movement of molecules?
It'll be 0.
They stop. They stop moving completely. So molecules don't have any movement at absolute zero. That's why it's called absolute zero. There's no more movement of molecules. So if the molecules aren't moving, how much pressure can they exert on the sides of the container if they're not moving at all?
0.
None. There'd be no pressure because the pressure is dependent on molecules moving. So if the molecules can't move, the pressure is going to be 0. So if we plot this, it should go through 0. Now this brings up another important thing I want to mention about gases. When we measure these things, we're going to be measuring pressure in a lot of different ways. We measure pressure in atmospheres. That makes a lot of sense because we know kind of what the pressure of one atmosphere is like. You know, it's like this. The higher and higher the pressure, the more, feels squeezed in. So one of the things we measure pressure in is atmospheres. We also measure it in something called torr, or millimeters of mercury. And we'll talk about this more when we do our, when we get to it in class. Basically, millimeters of mercury is how much pressure, if you leave a column of mercury with a vacuum above it and you let the atmospheric pressure push down on the mercury will rise into a column to about 760 millimeters high. And so you may have heard, sometimes you may hear on a weather forecast that the atmospheric pressure is like 754 millimeters or 768 millimeters. They also use a measurement called kilopascals. We're not going to talk too much about that, but there's lots of different measurements for pressure. Now, temperature, or for volume, we use the ones we're normally associated with. We use liters. So we don't have to learn anything new about liters, because liters we're familiar with. And temperature, what scale of temperature do you think we use for gases?
Kelvin.
That's right. We always use Kelvin for gases. And this is the reason why. Because unlike liquids and solids, the pressure of gases goes all the way down to 0 Kelvin. So when we're calculating things like pressure, we need to know what the temperature is in Kelvin, so that we can actually get that relationship between temperature and pressure correctly. It's one of the main reasons we use Kelvin in the first place, actually, is for measuring gases. So liters for volume, temperature is going to be in Kelvin, pressure is going to be a lot of different things. I think we're going to be using atmospheres for this particular experiment. And N, what are we going to measure N in?
Molarity.
Nope, not molarity.
Moles.
Molarity is capital M. Small n is
Moles.
moles, right? Small n is always moles. And so next experiment I think we do, what we're going to do is actually determine what measurement can bring all these things together. But for right now, we're going to try and figure out what the relationships are between each of them. Any questions so far on how we're going to measure gases? Everything should be fairly straightforward except for pressure, because we haven't really talked about pressure before. There's a lot of different, like physicists measure pressure in one particular way. Chemists measure pressure in a different way. Engineers, depending on what branch of engineering they're in, measure pressure in all sorts of different ways. But it basically comes down to force over a particular area. And it's just how do you want to define force and how you want to define area. That's basically what pressure is. Any questions so far? Okay. Oh, one question. How come we don't feel atmospheric pressure? Atmospheric pressure is actually a lot of pressure. How come we don't feel it?
Maybe something related to oxygen or the air.
It's something to do with the air.
Is it with the pressure we have in our bodies?
Exactly. Yeah, it's the pressure. You have the same pressure pushing out. So you don't really feel it. I mean, your whole body's full of, gases and everything. So you don't really feel it, but you do feel it when you go diving or when you go way up on like Mount Everest or something like that. So Mount Everest, the pressure is the atmospheric pressure is higher or lower when you go up to like the top of Mount Everest.
Higher. Lower.
Lower. It's a lot lower, actually. It's only about 60, between 50 and 60% of the pressure it is down at sea level, which is why you need to have oxygen, because basically you're breathing so hard that your body can't get enough oxygen because the pressure is so much lower. And if you go diving into the sea at lower and lower depths, what happens to the pressure as you go down there?
It's higher.
It's higher. It gets a lot higher. It gets dangerously high. So that you're so much pressure on your body that it actually forces gases out of you. That's how you get the bends. Basically, the dissolved gases in your body are forced out, and so you get all these like bubbles of gas in your bloodstream, and it's not good. So that's why.
Sorry, I cut you off.
No, go ahead.
So if you were to go in a water, is that why sometimes you get ringing in your ears?
Yeah, like you go down to the bottom of a pool.
Yeah.
And you feel your ears ringing. Yeah, that's the pressure of the water pushing in on the tympanum of your eardrum. It's pushing it in. You can feel that pressure, and that's only like at what, 10 feet of water. So you could imagine what it would be like 100 or 200 or 300 feet. So that's why when divers go in, they go very slowly. They don't just jump in and go right down to the bottom, or else their eardrums would rupture. So they sort of go slowly and let their body equilibrate to the pressure. Anyway, so let's have a look at the experiments we're going to do. These are kind of fun. So here's the website. So can everyone get to the website? Hopefully it'll work for everybody. We're not going to be stuck with. Oh, where is? All right, can everyone see the screen I've got here?
Yeah.
Okay, I've got mine going. Everyone got theirs going too?
Yeah.
All right, cool. So, number of different things you can see here. You see a piston. I sort of talked about a piston a little earlier. That will allow you to change the volume. We've got a heater underneath this piston, and we can turn it on, and it raises the heat, or we can cool it down, and it makes the temperature go down. Okay? So what I want you guys to do is basically change the different parameters and then see what effects they have on, like, we're going to change, like, basically we're going to put in, the first experiment is Boyle's law. And so we're going to look at with Boyle, what's the effect of volume on pressure. We're going to change the volume and then see what effect that has on pressure. So you can see that our temperature is in Kelvin and our volume is in liters. So liters we understand, Kelvin we understand. Our pressure will be in atmosphere, so we don't have to worry too much about that. Now, energy over here, kilojoules per mole. Anyone know what KE stands for? Anyone taken physics? If something's in kilojoules per mole, we know E is energy, because joules measure energy, right? So what's K going to be?
Kinetic.
Kinetic, very good. Kinetic energy. So that's basically going to be a measure of how much energy I'm putting into the system by increasing or decreasing the temperature. When I increase the temperature, the kinetic energy is going to go up. When I decrease the temperature, the kinetic energy is going to go down. And this is going to be measuring the actual speed. This will be the speed of the molecules in meters per second. So you can see as I increase the temperature, the speed of the molecules goes way up. And as the speed of the molecules goes up, my volume goes up. So what I'm going to do for the first reaction is, let's clear all this stuff off. So we're going to, like, pick a temperature. It doesn't matter. You can pick whatever temperature you want. I'm going to try and get it to as close to room temperature as possible. What's room temperature? Anyone remember in Kelvin?
Is it
Like,
273?
Yeah, it's around 300. It's about 298. So I'm going to see if I can get it to about. That's close enough. 305. That'd be like a warm. That'd be a warm day. So I'm gonna lock in my temperature there. Okay, and then I'm going to evacuate all the gas. And this little knob down here, that knob down there, if I click on it, it basically evacuates the cylinder. And so you can see what happens to the cylinder when I evacuated it. Also showing you the relationship between moles and volume, right? Now that my moles are 0, what's happened to my volume?
0.
It's 0. Yeah, so I have no gas. I have 0 gas in there. So my pressure is 0 and my volume is 0. There's no there's no gas. So there's nothing to have pressure. So what I'm going to do is basically I'm going to put in 2 pumps of gas. So I go over here to the little pump. So this is the pump over here, right? And I'm going to give it a couple pumps of gas. And you can see I've got 2 different gases. And you can see the 2 different gas molecules are 2 different sizes. Gas A is smaller. So gas A would be something like, let's say, neon, which is or hydrogen, which is pretty small, or helium, which is really small. And then gas B is bigger, something like xenon, which is a lot bigger than neon or helium. And so you can try different sizes of gas molecules and see if you get a different result. You know, I think that's in one of the instructions, is try a different gas and see if you get a different result. Actually plotted on the same graph. So let's put in our 2 pumps of gas. I'm going to put in 1, 2. And you see it goes right to, fills it up completely. So I've got 1,000 liters. Now, what I want to do is push the piston down so that my volume decreases. And we're going to see what effect that has on the pressure. But now what I want to do is start taking data. That is the whole point of this experiment, by the way. So I make a note of what's my temperature. So my temperature is 305 K. Yours will be whatever, I don't know what temperature you're going to use. You can use whatever temperature you want. Okay, just make sure it's the same temperature all the way through. And so my first data point would be when I'm plotting volume in liters.
Professor, do we put that on the Charles law or the Gay-Lussac's law, the recording?
I'm sorry?
Are we recording on the chart where it's listed Charles law or the Gay-Lussac's law?
Oh, I think we're doing Boyle's law first. Looking at the relationship between volume and pressure.
Oh, okay.
So I make a data table, and I mention in the data table what my temperature is, and I make my first data point. So when my volume is 1,000 liters, the pressure is 1.5 atmospheres. So that's my first data point, right? So now I'm going to reduce.
Our values are different, right?
Yeah, it's going to depend. It's going to depend if your temperature is different, your value is going to be different. It may be different if you use a different gas. That's why I want you to try different gases and see what the effect is. So I'm going to reduce my volume to 800. So at 800, liters, my pressure is 1.88 atmospheres. Then I'm going to go down some more. Go down to, right, at 610 liters. And obviously you can pick whatever you'd like. I kind of like to do the full range so that I can make my plot as big as I can. So at 610, I've got 2.46. Okay, make a note of that. All right, so 280. 280 liters, I've got a pressure of 5.36. And you can use 5, you can use 6. I think it's recommended you use at least 5, but you can do more. You can take more data points. The more data points you take, the better your graph is going to be. I recommend 5, but you can do more. You can do 10 if you want. So looks like the highest I could drop it down to is 150. So at 150 liters, my pressure is 10.01 atmospheres. Now, why that may be the case is that on a lot of gas cylinders, there's a pressure regulator on the top. I use gas in experiments all the time. So I've seen a lot of gas cylinders, and they have what's called a regulator on the top. And if you exceed a certain pressure, it lets off pressure. And so it looks like this particular gauge is limited to 10 atmospheres. So probably if I go above 10 atmospheres, it will vent gas until I get back down to 10 atmospheres. So here's my data. Does everyone know how to use like a graphing program like Excel or something like that? Have you used that before? Should we sort of have a quick review on how to use that?
Yes, please.
Sure, let's do that. Since that's kind of an important part. So I'm going to take my, I'm actually going to have to write my data down now. So 1,000, 800, 610, 280, 150, 1.5, 1.88, 2.46, 5.36, 10.01 liters in atmospheres. Okay. All right, so what I'm going to do is go to, I've got Excel open. If you don't have Excel, you can do the same thing in Google. I think Google has a program, but that's much the same. Or you might have freeware that does the same thing. They're all pretty much the same. So what I want to do is set up. Can everyone see my spreadsheet?
Yes.
Okay. Now you have to forgive me. I don't like Excel. It's sort of like it's evil, and I hate it. But you know, that's basically it's what we have. So what I'm going to do is I'm going to put in my two bits of data here. I'm going to have volume in liters. And then next to it, I'm going to have pressure. And that's going to be in atmospheres. All right. And just to be fancy, I'm going to put, underline them. Okay. So my first data point was 1,000. So I've got the, you can see you can put the units, because when you're taking data like this, you got to have units, right? I keep harping, units are important. You can have the units here, or you can put the units in the numbers. It's probably better off to just leave the numbers alone, because when you plot it, I think the computer freaks out if it sees numbers and letters. So I normally just leave the units at the top in the description. So I have 100. So these were my volumes. So 100, 800, 610, 280, 150. And my pressures were 1.50, whoops, not 15, 1.50, 1.88. And now notice that the computer did not care that I had 1.50, because if it sees a trailing zero, it just assumes it's not going to affect its calculations, and so it leaves it out. But when you report your data, you have to remember that zero was there, that you had 3 significant digits in all of your data, except for the last one when you actually had 4. So 1.88, 2.46. 5.36 and 10.01. All right, so here's our relationship between volume and pressure. So we can see, do we have a direct relationship here or an inverse relationship here?
Inverse.
We have an inverse relationship here. So if we were to plot these two things as just volume versus pressure, it's not going to be a straight line going up. Actually, let's have a look and see what it looks like. So to see if I can remember how to actually plot these things. So I want to insert. I want to insert. Wait a minute, where is my plots? This isn't helping. Oh, data, under data.
Is it okay if we use Google Sheets instead of
Oh,
Excel?
it sure is. Yeah, you can see it's been a while since I plotted something
If you
on.
go insert, then you will see chart. Click on insert.
There it is. Yeah, there it is. Yeah, this is a new version of Excel, and they've moved everything around on me. Yeah, so what I want is a line. I want a line column. So I just click on this chart, and basically I want just a. Here we go. So you can see, what it does is sort of gives me a line that goes down. So it's this, actually, it's what it's done is it's plotted them in the wrong, damn thing. I want switch. God damn it. I want that. Oh, here we go. That's what I'm looking for. Yeah, so I've got, I want to just put a scatter plot. Because basically it just takes the first column as X and the second column as Y, which is what I want. So here, it'll show you the relationship between the volume on the bottom and the pressure on as Y. And you can see that this isn't a straight line, that it's actually curved. So basically what we want to do is figure out a way where when I plot two things, I'll get a straight line. So what do you think I can do here to get a straight line out of this?
Start from 0.
Well, if I put 0, I can't really put 0 in here.
No, make the volume 0.
Yeah, but I don't know what the pressure would be. The pressure would be infinite at 0. So that's just going to move. That's just going to move my. That'll be a data point like way up here. So remember, this is an inverse relationship. So my relationship between volume and pressure is it's related to 1 over the pressure. What if instead of the pressure, I plotted 1 over the pressure? Maybe I get a straight line then. So let's try doing that. Let's erase all this stuff. So what I'll do, sort of move this out of the way. Move this out of the way. Now I'll take my pressure. What I'll do is give it 1 over that. So what I'll do is equals 1 divided by, and then I put in the name of the spot. And that's F5 is where my particular number is. Yours could be wherever. So it's F5. F5. Okay. So I want F5. Now I'm just going to drag down and it'll solve all of them for me. Okay. So this is 1 over the pressure. So you see how I did that? I can do all the calculations at once. That's like the one good thing that Excel is good at. I don't have to calculate all these by hand. I can just have Excel do it for me. So this would be 1 over pressure, and my units would be 1 divided by atmospheres. So I'm going to plot that. So let's see what happens. So this, my initial chart was volume over volume on the bottom, pressure. This time I'm going to plot volume versus 1 over pressure and see what we get. I'm going to go back to insert. I want scatter plot. Now look and see what I get. Now I have a straight line. Notice the difference. So I've got my volume on the bottom. There's my volume in liters. And so I will when I do my lab report, I'll either write it on there or you can just type right on it, change it. You can label these things. You know how to label the axes? Just type right on it. Are people familiar with Excel, or people have just been using Google for so long? Will Google give you the slope of the line?
Not that I've found.
Yeah, because it's important to get the slope of the line. So there's my volume on that side. And here, instead of pressure, I've got 1 over pressure. So that will be in 1 over atmospheres. And so notice what happens. Now I've got a straight line and it goes right through 0. So that's my relationship. My relationship is volume equals something, the slope of this line, let's call it M, over 1 over pressure. So let's look and see what the slope of the line is. And my slope will be God, I hate Excel. It should just show it. Formulas. I think that's it.
I was able to get a straight line, but then my X and Y axis are on the different side. My volume is on the dependent and my...
Yeah, but your volume isn't dependent. You didn't change the pressure and looked at the change in volume. You did it the other way. You changed the volume. So the volume has to be on the x-axis. Where the hell? God, I hate Excel. I used to know where to find these things. Oh God. Where do I find it? View data. Chart. That does not help me. Man, I'll have to figure out. Yeah, I forgot my Excel changed from the last time I used it. So now I don't know where anything is. I just made it so ridiculously complicated.
So, Professor, I have a question.
Yeah.
When we do the lab report, did you want us to graph it and then provide it in our lab report?
Yes. Yeah, you should have 4 different graphs in the lab report reflecting the 4 different things we're going to do. I just desperately need to find where to get the equation so you can show it.
Did you want us to put the equation on the graph as well?
If you can, I mean,
Yeah.
I can't find the damn thing. where is... Ah, damn you. Yeah, there used to be something called trend line. You just right click and it would give you the trend line and it would give you the equation. That is no longer the case. All right, so yeah, I'll just have to look up help or something. This is really sad.
So
Because
did you want us to do that as well? Because I couldn't find it on Google Sheets as well.
Yeah, whatever you use. I just can't believe I can't find it because it used to be so easy to find, but now it's been moved to make it more difficult to use. Microsoft is constantly making its software more difficult to use. I don't
Yeah,
know why.
it should be under series for Google Sheets.
Under series?
Yeah, for
Okay.
Google Sheets, it should be under series.
Is it format or insert or data?
Like customize, and then you go to series.
And it gives you the slope of the line?
It gives you R to the power of 2.
Yeah,
Oh,
I got
oh, that tells you how straight the line is. You need to know the slope. It should give you a y equals mx plus b. So the y will be, so the y is so y is equal to 1 over p, x is equal to v, and so y is equal to the slope of the line times the volume, and then plus b will be where the line hits the y-axis, which should be pretty close to 0. And I could show you that if this damn computer program wasn't the most evil thing in the history of the world. Oh, man. This sucks. No, it's just useless. No, sorry. I'm just gonna have to find it, and then post it or something. Because yeah, I can't find it anymore. It used to be so easy to find. Nope. Okay. Yeah, I give up. So, yeah, what I'll do is so you're gonna have to figure it out for Excel, and I will, or figure it out for Google Docs. I'll figure it out for Excel and then post it. But for right now, what I want you to do is have your charts, give the chart a title. So this would be volume, volume versus 1 over pressure. And then label the y-axis, label the x-axis. And then, at least if you can't figure out the slope, at least, join it with show that it's a straight line. That's what we're looking for. We're trying to figure out what's the relationship between these different things. We're basically trying to derive the laws as we know them. So by doing this experiment, we can clearly show that the direct relationship is between volume and the inverse of the pressure, or 1 over the pressure. That it's an inverse relationship between volume and pressure. Okay? Damn it. All right, so let's go back and do the next one. So for this one, the second one, we want to do Charles' law. So what we're going to do here is we're going to vary the temperature and see what the effect is on the pressure. So again, we want to empty everything out, and we can reduce the temperature to whatever we want. Let's say 95 or whatever it is you'd like.
Professor, how can you make the volume 0?
Just by letting all the gas out. You just hit this little valve on the bottom, right next to where the pressure is.
Oh, okay.
So when you click on it, it releases all the gas you put in there. All right, so I'm going to try gas B this time, see if it makes any difference. So gas B. So I'm going to put in 2 pumps of gas. 1, 2. Wait a minute. Oh, sorry. Here. Duh. 1, 2. And so the other thing I'm going to do is lock my volume in. So what I'm going to do is I'm going to change the volume, let's say to 500 or something, or 600. Make it whatever you like. You can even go all the way to 1,000 if you want, okay? Just pick a volume and then lock it. Hit the little lock. That way it stays at 1,000. Or if I want to reduce it, it's going to stay at 800. No matter what I do, that volume is going to stay the same. I can put more gas in, I can change the temperature, whatever, but that volume is going to stay the same. And that's important for this because in this particular set of experiments, we want to see what the relationship is between the temperature. God damn you. See what the relationship is between temperature, my relationship to pressure. So I have to keep 2 things constant. I have to keep the number of gas molecules the same. So I can't add any more gas and I can't remove any more gas. And I have to keep the volume the same. Because if the volume changes, I'll be changing both the volume and the pressure as I change the temperature, right?
So in that case, you fix the temperature and you fix the pressure and you
No, I'm going to fix just the volume.
volume, yeah. And
because
the
I'm-
temperature, yeah?
No, I'm changing the temperature and seeing what effect that has on pressure.
Oh, okay.
That's why I've locked the volume so it doesn't change. So you make sure that this little lock is connected. So so just click it and it'll stay locked.
Okay.
So then I just take my first data point. So that's 95K, 800 liters is going to be my constant volume, and my pressure is 0.58 atmospheres. So then I just hit heat and I raise the temperature. So I raise it to 265. And I see my pressure is now at 1.63. See, and you also notice, look on the right side, notice that my molecules are moving faster than they were before. You can also see it, you can visually see that they're moving faster as well. But you can also measure the speed at which they're moving. So I heat it a little bit more. So now at 350 degrees, it's 2.15 atmospheres. Okay, write that down. Heat it up a little more. So at 450 degrees, or 450 K, it's 2.77. Yeah.
Are you doing Guy-Lussac's law?
Charles.
I thought Charles is temperature to volume.
Oh, sorry, which one?
Isn't Charles temperature in relation inversely to volume?
Yeah, I printed everything out. Yeah, and you're right. Yeah, I printed everything out. I don't think I got the order of the pages right.
Yeah, so you're doing the Guy-Lussac's law?
Gay-Lussac's. Yeah.
Yeah. Okay.
Yeah, exactly. I had the pages in the wrong order. I apologize. But I have 4 data points so far. I'm going to get one more.
So this is Gay-Lussac's?
Yes. But presumably you guys are going to do this like afterward, right? It's not just. Right, so I have my 5 temperatures and my 5 pressures. So again, I will now go to my horrific Excel, which I loathe in every way. So I can probably just make a new sheet might be the easiest thing to do. And then just put in my temperatures. So temperature in Kelvin versus, oh, it should be capital K, oops. Capital K versus pressure in atmospheres. So my first one was 95, second one was 265, third one was 350, fourth one 450, and my last one was 565. And remember, everyone's data is going to be different. So 0.58 atmospheres, 1.63, 2.15, 2.77, 3.48. At least we'll be able to find the data a little faster this time. So now I want to scatter. And immediately you can see that this relationship is direct, which makes sense. Because you can see that as we increase the pressure, as we increase the temperature, the pressure also went up. So here's my pressure over here. Here's my temperature in Kelvin here. And it makes a straight line that goes right through zero, like it should. I mean, because it's a computer simulation, it should be perfect. So yeah, it goes right through zero, which is sort of why I recommend doing like as wide a range as you possibly can. So you get a good plot that way. You generally want to fill up your plot with as wide a range of data as you can. Yeah, I just have to, yeah. I don't know how many of you are using Excel. How many are using Excel versus Google? Pretty much everyone's using Google, right? Because it's
I'm
free.
using Excel.
Yeah, because that's, so do you remember how to find the trend line
I tried
for a
looking
scatter
it up.
plot?
If you look up on the search bar, it'll usually show up like right away, but I can't seem to find the trend line.
You can go insert.
Have you tried right clicking?
Have. Add chart element. Oh, here we go. Add chart element. Trend line. Linear. How do I do that? How do I do that?
Oh, are you talking about the line where it connects all of it?
Yes. Oh, there it
The
is.
dotted line? Yeah.
Yeah.
Yes, there it is. Okay, it's there now. But I want the slope.
Yeah,
Why
I
won't
don't
it
know
show
how
me?
to give
Why
the
won't it show?
slope.
That's the whole point. Format grid lines. Stupid piece of crap. Oh, show. Let me get my stupid face out of the way. Display equation on chart. Thank Christ. There we go. And the R squared. Gee, that was easy, huh? Yeah, so here's our y, finally. Here's our y and x. Here's our slope.
How did you do that?
That's a good question. So went up to trend line. Add chart element. I don't know where that comes from. Add chart element and scroll down to trend line and say you want a linear, an exponential, whatever. You want linear. And then more trend line options would be, and that shows up here on the right side of your screen. And you say, display the equation. And it gives you the equation. But I'm trying to find, where do we find add chart element? Where is that? That's not helpful.
I think
Yeah.
the chart then.
Because if you right click, it doesn't have add chart element. No, it doesn't. Yeah, so it looks like the only way that I can figure out how to do it is to do a search for trend line. And then it does it. But you're looking for add chart element, and I cannot find it anywhere. Because, yeah, who would want to, if you're going to plot something, who would want the slope of the line? That's pretty stupid. Nobody would want that. Anyway. Yeah, so this gives us our slope. So our slope is, right here. So y equals 0, 0, 0, 6, 2, and x is the temperature. So my pressure is 0.0062 temperature plus 0.0063, which is pretty close to 0, so you can pretty much eliminate it. So basically, you can just take the temperature in Kelvin, multiply it by 0.0062, and it will give you the pressure in atmospheres. Okay? Your slope may be slightly different depending on, let's see, if the gas is different, maybe the slope is different. That is possible. But yeah, but I would yeah, go ahead.
Question. What if we can't find it on Google Sheets? I'm like looking for it.
Oh, I'll find out a way and send it to you. I mean, I used to be able to know how to do it on Google Sheets, and I'll find out again. Yeah, let me. Go ahead.
I was able to put the equation and the R thing in Google Sheets.
All right, you want to tell us how you did it?
I went to go to edit the chart and then go to setup. Let me go back. And then
See if I can put mine in here.
Oh no, I went to customize and then series.
Wait, where did you get customized from?
When you click the chart, there's like 3 dots on the side. You just click that and then go to edit chart.
Oh, okay, I see it.
And then customize and then just scroll down. And it says trend line. And then click that. And then it says label and then there's use equation and then show R2.
I'm on customize, but I don't see trend line. It says chart style, chart and axis titles.
Oh, you click series.
Series. Okay.
And then go down and then you'll see trend line.
Do we use use
Series.
equation or R2?
I think both.
I have the trend line. I just don't have the slope, the equation.
And then you just scroll down and then it'll say none and then there's a drop down thingy there and then just press. I don't know if you see it, but mine says use equation.
Yeah, it should say label and then use equation.
Oh, wait,
Oh,
I
I see it.
think I have your sheet in here. Here. Are you sharing it? No. Oh, this was a while ago. Oh, it's a different. Okay. So I was gonna.
Sure. Do you want the R2? Do you want
I'll put up Google Sheets and you can talk us through it.
Do you want R2 and the slope or just the slope?
Just the slope. I mean, R2. That's R squared, by the way.
Sorry.
That just shows you how straight the line is, and it should be pretty close to 1.
So I have a question. For my equation, it has it under 5.85 e to the -3. That's okay if it's written that way, or do you want it written the other way? It's written in scientific notation.
That's fine. That's fine. Yeah, I just basically just want you to show me what the relationship is between each one. So do you want me to go through the Google spreadsheet thing? So I've got it up on the screen here. Or did everyone understand that particular explanation?
I was able to get it. I'm not sure of other people.
Yeah, I got it too.
All right, good. I'm pretty sure I did not, so. 0.58, 1.63. Because you guys have access to Google for free because you are students at Skyline. I'm not sure you want to because it's kind of hateful, but you know, at least it doesn't track you from space like Google does. All right, so I've got my temperature, I've got my pressure. So if I want to plot these, do I just
Insert.
select? Oh, insert. Okay.
Select the two.
I do select them. Okay.
And then insert. And then chart.
Insert chart. There we go. All right, cool. And then to get then I just scroll down here and there's a trend line. No, where's the
Go to customize
customize?
and then series.
Series. Oops.
And scroll down to trend line.
Okay.
And then
And
when you
scroll down again. And then click label none and then use equation.
Oh, perfect. Okay, there we go. Yeah, perfect. Yeah, and then basically, yeah, you would just, so on your plot, you would make sure you have the units. That's going to be important. So P should be in atmospheres, T should be in Kelvin. And yeah, just show, is there some way to show the actual data points rather than just the line? Can I see the data points as well? That's kind of important.
You should go to the like horizontal. You should go to the
Chart style?
yeah, chart
They want a
style, data chart.
Oh, plot. Oh, no.
Go to setup. Go to setup. And
Oh,
then
yeah, I don't want a line chart. I want a scatter. There we go. Yeah, you want a scatter plot, and then you would go back to customize to show that and get the trend line. Right. Okay.
Yeah.
Series and everything else. Right. Yes. You want a scatter. Make sure you do a scatter plot because it's important to see all the data points because everyone's data points are going to be different. So it's important that you want to see the data points. Okay.
are we doing the second graph as well for this for Gay-Lussac?
You're going to be doing 4. You're going to be doing four graphs. And I think maybe one of them even has 2, because I think one of them suggests you change the gas.
So
I think it might have
oils-
been a, I can't remember.
I think it was the one that we just did, right? That had 2.
Yeah, one of them is 2 different. Was it Avogadro? Did not have my pages numbered, which is a drag. Oh yeah, Charles' law. You do it with gas A and gas B, and you can just put those. You can put those on the same plot, actually. So with Charles' law, you change the volume and then change and see what happens to the temperature and the pressure, and then you try two different gases to see if it makes a change. So in that instance, you would just have gas A here, and then just put gas B there. Just put them on. You can put them on the same plot and see if they fall right on top of each other, or the slopes of the lines different.
I have a question.
Yeah.
In the lab report, are we going to do like separate graphs for each gas law, or
Mm-hmm.
okay?
Do
Yeah.
I need to include also the table, the data table, or
Yep.
just the graph?
Always. Yeah. You can't have a lab report without a data table. It's not a lab
It's a
report.
very long report. For
Yeah. Yeah, but I mean, it's all right there. I mean, basically you just need, introduction, what it is you're trying to do. And then basically you just answer all the questions that are inside the instructions. That'll be part of your discussion. And then your results are just like the data tables and the plots.
So no need for.
And then answer the post-lab questions.
How about a procedure?
Yeah, remember, all the procedure is very, very briefly. Just give a rundown of what it is you did. So basically, it would be like, for Boyle's law, I put 2 pumps of gas in. This was the original pressure, and then I changed the volume. That's it. I mean, I just changed the volume. And you're pretty much done. And then just go to the next one. So very briefly, you don't have to go into like minute detail of like, I changed it to this volume, and then I changed it to this volume, then I changed it to this volume, because that information's in the results. I don't need to know that. Just say you changed the volume. That's it.
So we need 2 graphs for Boyle's, 1 for Gay-Lussac's, 2 for Charles, and 1 for Avogadro's.
You can put the one with 2 different gases, you can put that in the same plot.
Okay.
Yeah.
So
Or you can have 2. It's up to you. If you can't figure out how to put two lines in the same plot, then just give me 2 plots. That's fine.
So in the lab report, we have to put the table and then the graph
Mm-hmm.
for each. Okay.
Yep. Yep.
For each graph, you want us to include the equation and the slope too?
If you can, yes, please.
Okay.
Yeah. Yeah, because basically what the slope does is it tells you what the relationship is. I mean, you can see, yes, I mean you can see that it's a direct relationship because it's a straight line. But the slope and the R² value sort of tells you that yes, it is very linear, and this is the relationship. I could just type in because when I have the graph, I could just type in a temperature, and it will tell me exactly what the pressure is. And then actually you can go back to the simulation and try that temperature and see how well it agrees. I mean, it should agree exactly.
So the R² is the slope then?
No, the R² tells you, the R² basically is a measure of how close your data fits to that straight line. So if it fits exactly to the straight line, you get an R² of 1. And so basically scientists use it when we do a plot. If we want to look and see what I'm doing a plot of like my real data in the lab. So I'll have my X here that I'm varying and have my Y over here. Then I'll do a plot of it. I'll get results that look like this, right? It's going to be all over the place because it's a real experiment. So then what I'll do is that I'll have the computer draw me the best straight line it can through there. And then it'll give me a slope, and it'll then give me the R². And it'll say the R² of this line is like 0.89. So then I'll look at that and say, well, yeah, it's a straight line, but it's not. Maybe there's a better way of looking at this data. And so I'll try a different plot. Maybe I'll try an exponential one, because maybe this line fits my data better. So I'll fit it to an exponential line and see what the R squared of that is. And if my R squared for the exponential line is like 0.96, then I'll say to myself, oh, this isn't a linear relationship. This is an exponential relationship. So you try all sorts of different plots until you get the one that gives you the best fit. And so R squared is a measure of what the fit of the line is. And if it's 1, that means it's 100% fit. You can't get any better than that.
So then you want us to calculate the slope then, using the equation that we have?
Well, the computer will calculate the slope for you. That's what the y equals mx plus b is. That's the equation that fits that line.
The slope is already in the equation.
Yeah,
Oh, yeah.
the slope is there. Yeah, the slope is there.
Got it.
It gives it to you in this form. So where y in this instance is the pressure, x is the temperature, and m is the slope of the line. It just tells you what the relationship is between x and y. And b is going to be really close to 0. In this instance, yeah, with this Google plot, yeah, you might want to put, yeah, it doesn't give you 0. I think it gives you the option of selecting 0. I like to have my axis start at 0. It's not necessary, but yeah, that's the way I like to do my plot, because then I see if it doesn't go through 0, there may be something else going on. Your plots should pretty much all go through 0 or very, very close to it. I think our B here was like 0.00069 or something, which is practically 0.
So how should we move the graph from the spreadsheet to the doc?
Oh, just copy and paste it, right? Can't you just copy and paste that plot?
Yeah, there's an option to copy the chart or download the chart.
Yeah, I just copy it. If that keeps all of your, if it keeps the line, if it keeps the fitted line and the slope, yeah, you can just copy and paste. Right? So if it's, hopefully, if I click on it and just say, copy, hopefully it will paste it somewhere else. I'm not that familiar with Google Docs. I use, as you can see, I use Excel. I'm a master of Excel. Been using it for like 30 years. I've never liked it. I've used such better graphic programs in the past. So, do you want to go back and do some more of the
Please.
the lab?
Yeah.
Because it's pretty straightforward once because they're all pretty much the same. You're just varying one thing or another. Where is my? All right. All right, here we go. So you can see the screen again?
Yes.
All right, good. All right, so let's see. So Charles. All right, so Charles' law, I don't think we've done that one yet. That's the result, that's the temperature and the volume for that particular one. So let's release all of our gas. And then it says to put 2 pumps of gas A in there. So I'm going to put, there's gas A, I'm going to put gas A in there. 1, 2. Oh, damn it, I keep doing that. 1, 2. And then reduce the volume to around 500 liters. Oh, got it right on it. And lock that one in. Oh, and actually don't lock it in. You take a, so then you note the, oh. Note whatever temperature you've got and the pressure you've got. And you may have started at, I don't know what temperature you may have started at. I started at 565 apparently, because that was the last temperature I used. So at this point,
So you can start at any
lower,
temperature.
yeah, you can use any temperature. I don't think it says, yeah, whatever temperature you want.
So do we keep anything locked or no?
No, this one you don't. We're gonna see what happens to the volume. I think the pressure should stay the same and the volume will change. So let's cool it down. Yeah, see that the pressure stayed constant and the volume decreased. So then we make a note. So at 565 or whatever my initial temperature was, the volume, then we note that the constant pressure is 5.56 atmospheres. So my second volume at 455, I went down about 100 to 100 Kelvin, and my volume went down by about 100 also. So I just drop it again, down to 345, and notice my volume drops by about the same. See, I think I see a pattern here. Then I go down to 235, my volume drops again. And finally down, and now we have a limit of the volume. It would appear at 150. If I keep cooling it, now the pressure starts to drop. So yeah, make a note of that, for this particular experiment, your volume should be between 1,000 liters and 150. If you drop below 150, then the pressure changes. That's an important thing to notice. So I can't go, for this particular experiment, I can't go below a certain temperature. So what I'll probably do is, select a pressure that gets you up to, I don't know, that probably would be a good pressure to use. And then just increase your temperature so you get close to 10, and then just start reducing your temperature. So you're free to select different temperatures, different pressures. Just be aware that with this particular experiment, if the volume is unlocked, just the volume will change, okay? And the pressure will stay the same until you get to 150 liters, it appears. So if I cool this down, notice the pressure stays the same, stays the same, stays the same, stays the same. Until I get to 209, the pressure's still the same, but I reduce it. As soon as it gets to 150 liters, notice the pressure drops. So you want to take all your measurements between 150 liters and 1,000 liters for this particular experiment.
Professor, I notice in my when I do this, like when I try to change the temperature,
Mm-hmm.
it moves very quickly. Like I cannot fix right away the temperature.
Yeah. You're not going to be able to select the exact. I mean,
Like I don't have control to change whatever I want to temperature to be exactly.
no. I mean, you can. Yeah, I mean, play with it for a little while. You'll be able to probably get it to within 5 or 10 degrees of what you want. But yeah, you only need like, 5, 6, 7 different data points. So you don't need, they shouldn't be separated by such a small temperature that the 2 points would be like right next to each other on the line. You want to spread your plot out as much as possible. So you want to get points in between 150 liters and 1,000 liters.
Okay.
Right. Any other? So is it,
And
everyone's
only one
clear on
piece
how to
of
do this one? So if the volume is locked, the pressure will change. And if the volume is unlocked, the volume will change. Okay? Make sure you're
Wait,
make a note
volume
of that.
unlocked?
If the volume is unlocked, it will change with the temperature. And the pressure stays constant until, well, watch what happens, until I get to 1,000 and watch what happens to the pressure. It goes up and 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 up till eventually, yeah, I think 600K is as high as I can go.
So for the lab, are we supposed to keep the volume unlocked or locked?
It depends on the experiment you're doing. If you're looking at the effect on volume, you want to keep the volume unlocked. If you're looking at the effect on pressure, then you want to keep the volume locked so only the pressure changes. Okay? It depends on what you're changing. Now for these experiments, you're either going to be changing the temperature and seeing the effect on volume or seeing the effect on pressure, or you're going to be changing the amount of gas and seeing the effect on volume and seeing the effect on pressure. So those are like the 2 things you can change the temperature, the volume, or the amount of gas. You don't have control over the pressure. That will vary depending on whether you change the temperature, the volume, or the amount of gas. But everything else you can change. Just be clear, when you're varying one thing, you got to make sure that other things are constant. You don't want to vary temperature and the volume at the same time. You want to vary one of them to see what the effect of that one thing is. So when we do our plot, we're looking at the effect of just one thing at a time. Do you think you're ready to do this one on your own?
Can
Yeah.
we do?
Right, someone's got a question.
So do I need to use the table that you created in the?
You can use whatever table you want. Those are just suggestions.
Okay.
Yeah, I
Professor?
mean, because basically you're going to be making your table in either Excel or Google Docs. Just use that, and just have the table right next to the plot. You don't have to write it out. Yes, question.
I have a question, but it's
Mhm.
not regarding this lab. It's regarding another lab.
That's fine.
I have a question on lab number 5.
Mm-hmm.
You were asked, or lab number 4, you were asking if the acid, which is H plus, and the base OH minus,
Mm-hmm.
if it's a product or a reactant in the
Mhm.
reaction.
Yep.
Does that still apply? Like if there's low amounts of it, then it'll be a reactant?
Did it change? Because that's the key, right? The key to that question is, and then the whole lab really, that if the concentration of something went down after the reaction, then it was a reactant. And if the concentration of it went up after the reaction, it was a product. So,
Oh, okay. So
so
from
the
the
question
initial.
was, well, yes, before and after. What was when you change the amount, when you change the amount of your reactants and products, does the concentration of H of H plus or OH minus change? Did any of them change?
Yes. If
They
it did.
did. Oh, okay.
So if it did, then, but if it didn't, then it's just, is it going to be a catalyst?
No, all you could say is if the concentration didn't change, then your products were neutral. They weren't acidic or basic. If the concentration of H plus went up, then one of your products is an acid. And if the concentration of OH minus went up, one of your products is a base. That's basically all you could say. And so I think the other question was, how would you be able to tell based on like the pH, right? So if you had if the pH went up, what does that mean? If the pH was a bigger number, if it went from 7 to like pH 10, does that mean it's more acidic or more basic?
More basic.
It's more basic. Yeah, that means you created a base. One of your products is basic. And if the pH went down, your solution is now more acidic. And so one of your products is an acid. We don't know which one. Or if it's only one product, if it's only creates like C, D, or A, or B, whatever, if there's only one product, we know that product's an acid. But I'm not sure the pH changed in any of them. Just have a look.
Okay.
You can go back and look at that simulation and see if the pH is generally 7 for all of them. At least it was for mine. I don't know. Maybe some of the products were acidic and basic. I wasn't sure. But just in case they were, I had that question in there because they might have been. I have no idea how many different molecules, how many different products you could make.
Sorry, quick question. Can you repeat what you said when you were saying if it's a lower H plus, then it's more acidic?
If there's a difference, now the P, let me write this, make sure you, because it's a little confusing. If the pH goes down, that actually means the concentration of H plus went up. That's the confusing part. Because the P in pH means basically 1 over the concentration. Okay, so if an H stands for the concentration of H plus, that's what the H stands for in pH, and P is 1 over. So if the pH goes down, it's 1 over the concentration, and so the concentration actually went up, and so it's more acidic. And if the pH goes up, that means my concentration of H plus actually went down and it becomes more basic. So if my pH went up, that means I made a base. One of my products is a base. And if the pH went down, that means it's more acidic and one of my products is an acid.
Okay, that makes sense.
Yeah. Oh, good. Because it didn't make sense to me when I was saying it.
All right, thank you.
No worries. Any other questions about either the lab today or anything else? We got a few minutes.
Could you please post the recitation number 6 today? Because just to prepare myself for the exam, I want to
I'll
review.
try. I don't know if I'll have time, but I will try.
Because I saw
Is number 5 been posted?
number 5, it's in YouTube, so it's fine.
Yes,
But
okay. So 6.
I need recitation number 6, please.
Okay.
When is the exam?
Friday. I'm going to post it at 10 a.m. and you'll have till 10 a.m. Saturday to do it.
And if the recitation is gonna be from recitation 1 to recitation 6, correct?
Mm-hmm. Yep. Yep. All right. Anything else? I think this is the best simulation of the bunch. I really like this one because you get to actually physically move things around and you get real data that you can plot, unlike some of the other ones. So yeah, I like this one. Any other questions about this one or any other one?
Oh, it's
before I
and please,
see it.
just review the answer, the one I told you, please. I'm curious to know the right answer.
Oh, yeah, on recitation number 4?
Yeah, question number
Okay.
7.
Okay, will do. Yeah, I've written it. I've written it in my big book of stuff. So
Okay, thank
I
you.
just circled it.
Okay, thank you so much.
Okay, no problem. All right, I will see you in about 2 hours. And we're gonna finish up chapter 4 in shapes, and then really briefly, don't want to freak you out too much. We're going to talk about a little different ways that molecules, that atoms actually share their electrons to form molecules, and hopefully that won't be too confusing. And then we're going to do gas laws after that. So, but now you're going to be experts at gas laws. We'll be able to zoom through that super quickly and then go right into thermodynamics, because I know everyone's going to love thermodynamics. Just the sound of it sounds fun, right?
Will the
Okay.
exam cover gas law?
No, the final will, but not this one. No, and it's because this is a lecture exam, so we'll only be covering stuff. Well, not only, but it'll be chapters 1 through 3 that we've covered in lecture.
Okay, Julie said you can pick me up.
Okay. All right. I'll see you in a couple of hours.